Very good morning to all of you. We will continue with our discussion in magnetostatics. We started looking at motion of charged particles in magnetic fields. So let me recall that the force on a charged particle consists of two parts: the electrostatic force plus the magnetostatic force. QE, this is the electrostatic force, and that is the magnetostatic force. So the electrostatic force, as we have seen, is directed along the electric field, and the force due to magnetic field is perpendicular to the direction of magnetic field. So we saw motion of a charged particle in a uniform magnetic field. So let me take a uniform magnetic field, say pointing into the page, which I draw as crosses here. So B is downwards. So let me assume I have a positively charged particle which is directed with a velocity v in this direction. Positively charged particle Q which has a velocity v in this direction. Now let me assume there is no electrostatic field at all. So the only force that will act on the charged particle is the magnetostatic force. So according to this equation, the force is perpendicular to the velocity and to the magnetic field, and it is along the direction v cross b. So v is in this direction, b is into the page. So as you can see here, v cross b is upwards. So the force that is acting on the particle is like this. This is the magnetic force. So the particle will tend to curve upwards, but as the particle curves, the direction of velocity keeps changing. So at this point, the force is directed like this. So the particle, as we have seen before, executes a circular motion, and the magnetostatic force provides the centripetal force for this circular motion, and we can write, for example, as we have seen before, the centripetal force mv square by r is equal to q into v into b. Here the velocity and magnetic field are perpendicular to each other, so v cross b is simply v times b, and that gives me the radius of the circular orbit as mv by q times b. So that's the radius of this circular orbit. So the particles will keep circulating along a circle. You can similarly do the same problem assuming that the charge is negative with the same direction of magnetic field, and find out what is the direction of motion of the charged particle. This radius also tells me that the angular velocity of the motion is nothing but v by r, which is equal to q b by m. Angular velocity is q b by m, and it's independent of the radius of the charged particle's motion or of the velocity. And this gives me a frequency of number of revolutions per unit time as f is equal to omega by 2 pi, which is equal to q b by 2 pi m. And this, as we have seen before, is called the cyclotron frequency. And is independent of the radius of the circular orbit. That's a very, very important aspect, and we will use this property to consider an accelerator, particle accelerator called a cyclotron a little later. So in the presence of a uniform magnetic field, a charged particle here, as we have seen, if the velocity of the particle is perpendicular to the direction of the magnetic field, performs a circular orbit on a plane, and that plane is perpendicular to the magnetic field. Now if you have both a magnetic field and an electric field, as we have seen last time, suppose I have a plate here which is positively charged, and I have another plate here which is negatively charged here. So it's like a parallel plate capacitor, and I have an electric field pointing downward here, and suppose I have a magnetic field pointing inwards, and if I project a particle here, then as you can see here, if the charged particle is positive, then the electrostatic force on this particle is downward, which is equal to q times E, and if the charged particle is positive, then the velocity is in this direction, magnetic field is downward, V cross B is upward, so the magnetic force is upward. So this is q V times B. So magnetic field is uniform and pointing inwards into the page, and the particle comes from here. So the net force acting on the particle is QE minus QVB or QVB minus QE, and it is perpendicular to the direction of this. Now, if the magnetic force is larger than the electric force, if QVB is greater than QE, the particle will tend to curve upwards. If QE is bigger than QVB, the particle will tend to curve downwards. But if QE is equal to QVB, then the net force acting on the particle becomes 0, and then the particle will go undeflected straight. And that means the particle, if the particle has a velocity v is equal to E by B, then the particle will go undeflected along a straight line. So only those particles which have a velocity equal to E by B, E is the electric field which is applied between the parallel plates, and B is the uniform magnetic field perpendicular to the electric field and perpendicular to the motion of the particle, then those particles will go straight. And if I happen to, for example, put a slit here, then those particles whose velocity is higher will be tending to go upwards. Those particles which have velocity lower will go downward, and only those particles which have velocity v equal to E by B will go straight through the slit. And so what will happen is the particles coming out from here, the charged particles coming out from here will have a velocity defined by v is equal to E by B. So it's like a velocity selector. You may have particles entering this region in this direction with different velocities, but only those particles with a velocity equal to E by B will be able to cross through the slit, and I will be able to select from this given set of particles those particles which have a different velocity is equal to E by B. So that's like acting like a velocity selector. Now, the motion of these particles in electric and magnetic fields was used by J.J. Thomson, Joseph John Thomson, 1856 to 1940, also referred to as J.J. Thomson, who discovered the first subatomic particle, namely the electron. He did experiments on cathode rays and showed that there are particles which are propagating in the cathode rays consist of particles which have much less mass than the known particles at that time, and he discovered the electron for the first time. And for this discovery, he was awarded the Nobel Prize in 1906. So what is his experiment? Let's see his experiment. So there is a discharge tube. So let me draw a discharge tube here, and then you have. So this is a tube which has low pressure gas. There is a metal electrode here called cathode, and then you have an anode here. And between these two, we apply a potential difference. And then you have another aperture here, and here I have a pair of plates in which I apply a positive voltage here and negative voltage here, and there is also a magnetic field into the plane of the paper here. Now, what happens is this cathode emits, when the cathode is heated, it emits particles which we now know are electrons. These electrons then get accelerated in the electric field existing between the cathode and anode, and the after the anode, through the hole in the anode, the electrons pass through the hole and then pass through this aperture here and enter a region in which there is crossed electric and magnetic fields. So the electrons are entering from here with a certain velocity. Now, if I do not apply any electric or magnetic field, then the particles will go straight and hit this point. And this point, there is phosphorescence in this point, and you see a green spot of light generated by the electrons which are striking the end of the tube. If you apply an electric field, then because the electrons are negatively charged, the electrons will move like this and go here and hit some other point here. So, in the presence of electric field only, you will see that the particles are bending and hitting another point on the exit end of the tube. Now, if I apply a magnetic field, you see that the electrons are moving in this direction. So, because this is positively charged here, the plate, so the electrostatic force is upward. V cross B is downward, but because the electron has a negative charge, the magnetic force is downward. Please note, the magnetic force is Q V cross B. V is in this direction, B is downward, so V cross B is upward. Because charge is negative, Q V cross B is in the minus direction here, in the downward direction. The electrostatic force is upward. So, if I have a velocity equal to E by B, then the particle will go straight and hit the same place as at the same place where there was no electric and magnetic fields. So, what I can do is the following, that for example, first let me consider the situation when I had only the electrostatic force. So, let me draw a figure here. So, I have positively charged plate here, negatively charged plate here, and the electron, this is the axis here, the electron comes from here and go like this and go straight. So, in this length, overall length L of this electrode, the electron has a net electrostatic force in the upward direction, which is so the force on the electron is equal to so let me in the upward direction. So, let me just write the scalar is equal to mod E times E in the upward direction. Now, this force will tend to shift the electron trajectory in the upward direction. So, this is similar to a motion of a particle in a gravitational field. So, the net acceleration in the upward direction is equal to mod E by m, force by mass, that is the acceleration in the upward direction. So, remember, the particle had 0 velocity in the upward direction here and it moves like this. So, let me call this displacement as d. So, what is the displacement? So, this is a particle moving in the acceleration is upward direction, the initial velocity in the upward direction is 0. So, you can calculate the displacement. So, if the velocity of the particle is v in this direction, time taken to propagate a length L is equal to L by V. That is the time taken for the particle in going from here to here. Within this time, the particle has a force applied in the upward direction. So, it will accelerate in the upward direction with the net result that the displacement d can be calculated as d is equal to half of acceleration into t square. Remember the formula, s is equal to ut plus half a t square. The initial velocity in the upward direction is 0. The acceleration is mod E by m, and the time taken is given by L by V. So I can substitute all this here. So I get half of the acceleration is mod e by m into t square is L square by v square. So I can relate this equation as mod e by m is equal to 2 d v square by e into L square. Mod e by m of the particle is equal to 2 d v square by e L square, and if I had chosen, so I can now calculate the velocity of the particle by finding out what is the magnetic field required to bring the particle back at this point. So I have an electric field here. In the absence of magnetic field, the particle trajectory is upwards. It displaces by displacement d here. Then I apply a magnetic field and bring the point back here. So I know the magnetic field required to bring the point back at this point, and that magnetic field must be related to velocity and electric field through this equation v is equal to e by v. So I can substitute this v into this equation, and I get mod e by m is equal to 2 d by e L square into e square by b square, which is equal to 2 d times e by L square times b square. So note here that by knowing these quantities on the right hand side, the displacement d of the particle, the applied electric field, the applied magnetic field, and the length over which the particles are propagating, we can calculate E by m. And this is what Thomson did. He could actually obtain the values of E by m of these particles, which were at that time not known. The particles coming out from the cathode are accelerated down, and by doing this experiment, he could find out what is the value of E by m of these particles. And he found out that E by m has a certain value. Now, what he also discovered is that this value of E by m is independent of the kind of electrode that we was using, independent of the type of gas that is contained within the tube, independent of the pressure of the gas, independent of the velocity of the particle, etc. And he obtained the same value of mod E by m for all these particles, and from which he concluded that this must be another particle, a particle which is there, which is a component of all atoms, and that is the electron. That is the electron, and he obtained the value of E by m, which happens to be now given by E by m approximately 1.759 into 10 to the power 11 coulomb per kilogram. He found that the mass of this, the charge to mass ratio is very, very large compared to the charge to mass ratio of a ionized hydrogen atom, for example, and he concluded that these must be particles, subatomic particles, which are extremely light, and that is the electron. So that was the first time a subatomic particle was discovered by Thomson, and for which he was awarded the Nobel Prize in 1906. So that's a very, very important discovery at that time, to show that electron is a constituent of all atoms and forms a very fundamental particle. Now, continuing with this experiment, he and his students developed another instrument called the mass spectrometer. So let me draw the a schematic of the experiment of the apparatus here. So I have a slit here, and I have ions coming from here. These are positive ions, and let me assume the charge is q and mass is m. So these are positive ions. These are ionized by some mechanism, and these positive ions are coming through the slit here. And I have in this region, again, just like before, an electric field. This is positively charged here, let me assume, and this is negatively charged. And I have a magnetic field pointing towards me. Uniform magnetic field pointing towards me. And I have another slit here. So as we discussed just now, only those ions. So there are ions, these are positively charged ions which are coming down. So the electrostatic force on them will be to the right, because they are positively charged, they are attracted to the negative plates of the capacitor here, and because they are going downwards and the magnetic field is coming towards me and they are positively charged, QV cross B is to the left. So magnetic force is to the left, electric force is to the right, and if I satisfy the equation V is equal to E by B, only those particles which have this velocity will be able to go through the slit and come out from the other side of the slit. These particles are coming out from here. Any particle whose velocity is different from this number will either be deflected less to the left or to the right and will not be able to pass through the slit. So this is, as I said, a velocity selector. It picks up those particles which have a very different velocity equal to E by B. So these particles are coming out from the lower slit, and I have a region here in which there is again a magnetic field. So let me draw a region here. This region has a magnetic field. The magnetic field is again pointing upwards towards me. Let me assume a uniform magnetic field throughout here. So this magnetic field could be the same as the earlier magnetic field or could be different. So let me just assume that there is some magnetic field here, B prime. A B prime magnetic field pointing upwards towards me. Now in this region there is only a magnetic field and there is no electric field. So as we have discussed before, these particles will now have a circular trajectory. So as you can see here, so V is downward, B is upward, the particles are charged positively, so V cross B is to the left, and these particles will now have a circular path like this. That's a semicircular path here. So from here it comes like this and comes here. And so let me call this distance as x, and x must be equal to 2 times the radius of the circular orbit of the particle, and we have already seen the radius is mv by q times b prime here. B prime is a magnetic field, and so I get x is equal to 2 mv by q b prime. So the position at which the particles will come and hit on this plane here is determined by 2 mv by q b prime. X is the distance from this slit here. So that distance depends on the charge present in the ion, the mass of the ion, and the velocity and b prime. Now velocity is already known to be E by B, so I get the displacement x is equal to 2m E by q b p prime. So knowing the values of, for example, if I measure x in this experiment, if I can measure x, if I know the value of x, then I can find out. So usually these ions are having a charge plus E. That means from these atoms, one electron has been removed, resulting in an ion which has 1.6 10 to the power minus 19 coulombs of positive charge. It has one electron left. It was neutral. You remove one electron, and it has remaining positive charge of plus E. So this Q is equal to mod E, and so I get M is equal to mod E B B prime x by 2 times E. So as you can see here, if I can measure all these quantities, if I know that it is a singly charged ion, if I know the magnetic fields B, B prime, and electric field E, which I have applied here, and the displacement x, I can measure the mass of the particle. So if you now have ions here entering with different masses, for example, another ion with a slightly different mass will have a different radius of curvature and come and hit here. So if the mass is less, x is less, and a lower mass ion will come and hit here, a higher mass ion will go here, even a higher mass ion will go with a larger radius of curvature. Now, so actually what you are finding is on the screen now, on a screen here, you will see particles hitting at different points depending on their masses. If all of them have the same charge q, particles having different masses will come and hit at different points here, and by knowing the position of these particles which are appearing here, I can actually estimate their masses. So if you have ion source here in which there are ions with multiple masses coming, then this particular structure will separate these masses into different points on the screen, and you can actually find out what are the types of masses present here and so on and so forth. In fact, this is the mass spectrometer which tells you what are the mass components present in the ion source that you are having. And incidentally, this is the first experiment that led to the discovery of isotopes. The isotopes, you know, are the same atoms with different number of neutrons, the same number of protons and electrons. So you can have, for example, hydrogen, tritium, deuterium, they are all isotopes. Similarly, you have isotopes of other elements, and J.J. Thomson along with his student Francis Aston did experiments using this kind of a setup and discovered the first isotope of neon. And so because they obtained for the same neon, they obtained two spots of 2 points where the ions were coming and hitting, and that implied that there were two kinds of ions, and they found their masses are slightly different, and that led to the discovery of the isotopes itself. So looking at motion of particles in charged in electric and magnetic fields gives us very interesting techniques to understand their behavior and also to analyze ions and measure their charge to mass ratios or masses if you know the charges and so on and so forth. So now all this time we have been looking at a situation where the velocity of the particle is perpendicular to the magnetic field. Now what happens if the velocity is not perpendicular to the magnetic field but is at an angle? So I will now discuss what results is in a helical path. So I want to consider a situation. So suppose I had a magnetic field coming pointing towards me, and if I had a charged particle which is going up here, if this is a positively charged particle, you see that this will have a circular motion like this, q. A positively charged particle, it will have a circular motion, and the radius is determined by r is equal to mb by q times b. That is if the velocity of the particle is perpendicular to the magnetic field. Now what happens if the velocity is not perpendicular but is at some angle? So let me draw a magnetic field here like this. If we call this as z axis, and let this be the x axis here. Let me assume I launch a particle with a velocity like this, and this angle is phi. Now as you can see here, the velocity is not at right angles to the magnetic field, but I am shooting a particle with a charge q. Let me assume a positive charge q at an angle theta with the perpendicular to the b vector. So I can write here b vector is equal to b times k cap. B vector has now two components, x component which is v cos phi and a z component which is v sin phi. The velocity of the particle has two components, one perpendicular to the magnetic field which is v cos phi, one which is parallel to the magnetic field which is v sin phi. So what is the magnetic force on the particle? Q v cross b, which is equal to q v cos phi I cap plus v sin phi k cap cross b k cap. Now k cap cross k cap is 0, I cap cross k cap is minus j cap. So this is equal to minus q v b cos phi j cap. So the magnetic force on the particle is minus q v b cos phi j cap. It's in the minus y direction. So y direction is pointing upwards here. So the minus y direction is pointing downward here. So if I use the right-handed coordinate system, x is like this, y must be towards me, so that z axis is like this. So the force on this particle is downward, and remember here the force only depends on v cos phi. And what is v cos phi? V cos phi is a component of the velocity perpendicular to the magnetic field. So this force will now make the particle go in a circular orbit, circular path. But remember, the particle also has a velocity along the magnetic field direction. So what's going to happen is the particle will be made to rotate in a circle because of the magnetic field and the perpendicular component v cos phi. It will be projected in the direction of the magnetic field because of this component v sin phi, and so it will form what is called as a helix. So it will look something like this. So the particle will move something like this. This magnetic field. So this circular path is because of the component of velocity perpendicular to the magnetic field. The motion along the magnetic field is because of the parallel component of the magnetic field. So we have, for example, v cos phi is v perpendicular and v sin phi is equal to v parallel. This is the perpendicular component, perpendicular to magnetic field component of velocity, the component of velocity parallel to the magnetic field. So the radius of this circular path is equal to m v perpendicular by q times b. That is the radius of this path. Now the particle completes one revolution in a time t given by 2 pi by angular velocity, which is 2 pi r by v perpendicular, which is equal to 2 pi m by q times b. This is inverse of the cyclotron frequency. The time taken by the particle in completing one circular path is t is equal to 2 pi m by q b, and in this time the particle would have moved a certain distance here. And so distance moved along z direction in time t is equal to v parallel into t, which is equal to 2 pi m v parallel by q times b. This is called the pitch of the ellipse, of the helix, pitch of the helix. So I have a demonstration here which will show you what is the meaning of particle motion in a helix. So I have actually, I brought a coil here, and I have a small nut in that, which is, as you can see, which is moving downward. That's the motion of the particle along a helix. As you can see here, the particle is rotating along a circular path, but is also moving horizontally, vertically in this case here. This motion is of course not due to electric and magnetic fields, but it is primarily because of the gravitational force here, and I am restricting the particle to move along the helix by simply having a spring here. So that is a good way to imagine the motion of a particle in a helix. As you can see here, that dark nut which is moving here is something like what the electron will be doing as it moves. So that's the helical path of the particle here. So the particle moves like this in a helix, and that is the motion of a charged particle when the velocity of the particle is not perpendicular to the magnetic field, but has a component also parallel to the magnetic field. So the perpendicular component of the magnetic field decides the radius and the time taken to complete the one circle. The parallel component decides how fast it moves along the direction of b. Let me take an example here. Let me take a particle with velocity of about 10 to the power 6 meters per second, a charge which is the electron, which is one electronic charge, and let me assume an angle of phi is equal to 45 degrees, a magnetic field of 5 10 to the minus 4 Tesla, and the mass of the particle is 9.1 10 to the minus 31 kilogram. So the pitch is equal to 2 pi m v parallel by q times b is equal to 2 pi into 9.1 10 to the minus 31 into 10 to the power 6 into cos phi is 1 by root 2 divided by 1.6 10 to the minus 19 into 5 10 to the minus 4, and that comes out to be about 5.1 centimeter. So that's the pitch, that is the distance moved along the direction of magnetic field in one circular revolution. And so that is a typical example where you can see here the particle will do like this and go upwards along the direction of the magnetic field. The helix will be oriented along the direction of the magnetic field. So that's the trajectory of a particle in a when the particle is not having a velocity perpendicular to the magnetic field, but has also a component parallel to the magnetic field. The perpendicular component makes it rotate in a circular orbit here, and the parallel component makes it move in the direction of the magnetic field, so it goes like this, and that's a helix. So we have seen some examples of particle trajectories in the presence of magnetic fields, in the presence of cross electric and magnetic fields, in the presence of a magnetic field and the velocity not being perpendicular to the magnetic field, but in some other orientation. Now, so as you can see here, the electric field can actually has a force which is along the direction of velocity of the most of the particle, and so it can accelerate the particle. The magnetic field has a force which is perpendicular to the velocity component and cannot speed the particle up. Now, there are what are called as particle accelerators. Which I would like to discuss. Particle accelerators have been investigated for the past more than 80 years. There are many accelerators in various countries, and these accelerators are used to accelerate charged particles for various applications. These have applications in semiconductor industry, they have applications in medical diagnostics, they have applications in cancer therapy, they have applications in pharmaceutical research, and so on. So there are many applications of particle accelerators, and the most famous accelerator is the accelerator in CERN, where the discovery of the Higgs boson was made. This is an acronym for Conseil européen pour la recherche nucléaire. It's in English, it's a European Council for nuclear research. So in this is an accelerator which is in Geneva, in the border between France and Switzerland, and it's an accelerator which is used to accelerate protons. And it's interesting to know that the particles are accelerated, protons are accelerated to a velocity, to a speed which is 0.999999990 times velocity of light in free space. 0.999999990 times velocity of light in free space, and that is only 3.1 meters per second slower than speed of light in free space. Extremely high acceleration, extremely high energies. These particles are having extremely high energies. Their velocities are very close to the velocity of light in free space. There are many accelerators in India, and I would just like to mention to you main some of the main accelerators here. There is IUAC, which is Inter-University Accelerator Center in Delhi. There is VECC, Variable Energy Cyclotron in Kolkata. Then there is an accelerator in RRCAT, Raja Ramanna Center for Advanced Technology. There is an accelerator in TIFR BARC, that is Tata Institute of Fundamental Research. And Bhabha Atomic Research Center. This is in Mumbai, and this is in Indore. These are some of the major accelerator facilities in India, and many of these accelerators are extremely efficient and highly functional and are used by various researchers in the country for various applications. I want to show you the construction of a cyclotron. So, let me draw it here. There is a cylindrical structure like this. This is, let me draw the complete figure here. So, this is, and there is another one like this. And then there is a magnetic pole piece here. There is another magnetic pole piece on the bottom. So, these are electromagnets. This is also electromagnet. Then you have a source of particles here, and the particles, as we will explain, go in a path like this, helical path like this, and come out. And these two are called Ds. They are in the shape of a D, but there are actually it is a made of copper, and in the hollow space between the two upper and bottom copper plates, the particles are revolving around, and these two magnets create a magnetic field perpendicular to the path of the particles, and there is a, these two are connected to an alternating current source. So, the electromagnet produces a magnetic field perpendicular to this, the Ds. The electric field is applied between the two Ds here, and as we will explain, the particle then can be accelerated in this path and comes out of the of this device in this target. And these are the charged particles, the charged particle path of the So, we now discuss about the how does the cyclotron work. Remember, we had defined a cyclotron frequency before. So, this is an accelerator which is called the cyclotron, and let me just draw you the construction of the cyclotron. So, there are two what are called as Ds, which are made of copper. So they are thin cylindrical thin structures, and there is a magnetic field applied perpendicular to this plates. So these are two thin sheets here, between copper sheets here, and there is space in between them, and the particle is actually moving within the plate. And these two plates are connected to an oscillator. Which actually applies an electric field between these two Ds, and time varying electric field, a sinusoidally time varying electric field between the two plates. So the potential is positive negative, then negative positive, positive negative, sinusoidally oscillating, just like our alternating current that we get in our power supply. So here is an oscillator which applies an electric field between these two Ds. There is a magnetic field perpendicular to the Ds here. Here I have drawn coming out of the page. So let me assume that there is a source of protons here at the center. So let me start by seeing what happens. Initially, let me assume that this is negatively charged on the left side. So proton being positively charged gets accelerated towards this D. Now it enters this D within the two copper plates, and because they are made of copper, there is no electric field within the volume within the space between the two copper plates. So there is no electric field penetrating this, and so this region of the D actually contains only magnetic field inside. So being a positively charged particle and a magnetic field pointing up, there is a magnetic force applied on this particle which makes it rotate along a circle and comes from here. It's a circular orbit of a certain radius which we have calculated before. Once it comes here, at this point what happens is I ensure that this now becomes negatively charged. This has a negative potential compared to this, so this proton gets accelerated towards this. When it enters this D again does not allow any electric field to be present inside. Now the velocity is slightly higher than before, so it makes a circular orbit like this, with a larger radius of curvature. By the time it arrives here, I ensure that this side is negatively charged, so the proton gets again accelerated. And then now the velocity is higher, so its radius of curvature is larger. By the time it comes here, this is negatively charged, it accelerates. So what the particle will do, if I have right conditions, it will rotate like this, and finally I can take it out of the system at some point. So what we are seeing is I am using the electric field to accelerate the particle when it appears between the space between the two Ds. I am using the magnetic field to make it circle along a circular path. Magnetic field does not speed up the particle, but allows the particle to take a circular orbit and come back to the space between the two Ds. The electric field between the two Ds ensures that the particle gets accelerated every time it comes to this space. Now this we have seen before, that the radius of the orbit is m v by q times b, and that radius depends on the charge, mass, and the velocity and the magnetic field between them. And we also have a frequency, cyclotron frequency, which we have defined before, is q b by 2 pi m. What is the frequency? This frequency is the time taken for one complete, the number of revolutions per unit time, or 1 by f will be the time taken for completing one revolution. And as you can see here, this frequency is independent of the radius of the orbit. So the particle will take the same time to come from here to here to the semicircle as it will take for this semicircle as it will take for this semicircle. All that is happening between the semicircles is the energy is increasing, velocity is increasing. As velocity increases, the radius increases. But because the frequency is independent of radius, the time taken for this particle to come from here to here is the same as the time taken for the particle to come from here to here. So now I must ensure that whenever the particle appears here in between them, the electrodes have the right potential difference, so that the particle gets accelerated rather than getting decelerated. So if when the particle arrives here, when it is coming out from this first circle, this part of the D must be negatively charged, negative potential, so that it gets accelerated. Now it comes here, and when it arrives here, this must be negatively potential, so it gets again accelerated. And every time it appears in the spacing between them, the potential must be such that the particle gets accelerated. And because the radius, the time taken for making this half a circular path here is independent of the radius of the curvature, radius of the particle motion here, this frequency is independent of the radius, whether you are looking at this particular path or this path. Now only under one condition, that is, none of these quantities on the right hand side change with the energy. Now we all know that mass is independent of velocity only at velocities much less than velocity of light in free space. So as the particle gets accelerated more and more, energy increases, velocity increases, and the mass will start to increase. So until you reach relativistic velocities, mass can be assumed to be independent of velocity, and in that case the cyclotron frequency is independent of the radius, and so I will need I would need this oscillator to oscillate at this frequency, so that whenever the particle comes here, the particle gets accelerated rather than decelerated. So that is the frequency at which I must operate. So this is the way the cyclotron works. A proton which is injected from here first gets accelerated by this plate being negatively charged. It enters this region where there is a magnetic field pointing upwards. That leads to a circular path of the proton. By the time it arrives here, this is negatively charged, so the particle gets accelerated again here, and then because now its velocity has increased, it makes a larger circular orbit. V is higher, so radius is larger. It comes from here. It takes the same time to propagate through this radius here, and then by the time it arrives here, this D is negatively charged. It gets accelerated again. Velocity increases, so the radius has increased. So it becomes a path like this, and at some point I can take the particle out by a deflector here. So that is the operation of the cyclotron, and it is used to accelerate particles. And so let me take so the key to operation of this is the fact that this cyclotron frequency is independent of the radius of the orbit. So this particle accelerator can be used for accelerating particles to high velocities, except that you can't go to relativistic velocities with these particles. So the oscillator frequency must be equal to f, which is equal to qb by 2 pi m, and the maximum energy assuming velocity of the particle to be much less than c is equal to half m b maximum square, which is equal to half m q square b square r square by m square, which is equal to q square b square r square by 2m, where r is the radius of the d of the cyclotron radius. So the maximum radius that the particle can have is this value of the radius of the d, and it comes out of the d with this energy, which is q square b square r square by 2m. We can look at one example here. So if you take protons, q is equal to 1.6 10 to the minus 19 coulomb. So let me take a radius of 0.2 meters. The mass of the proton is 1.67 10 to the minus 27 kilogram. I leave this calculation to you. The oscillation frequency is 21.4 megahertz. You can calculate. The maximum velocity comes out to be 0.27 10 to the power 8 meters per second. It is still 1/10 the velocity of light. The maximum energy is equal to 3.75 million electron volts, which is 3.75. And you can calculate the mass of the particle at this velocity is 1. There's a slight increase in mass because of the velocity being closer to the velocity of light, but that increase in mass is very, very small compared to the original mass. So what we have discussed today is the motion of charged particles in electric and magnetic fields, how the charged particles revolve around a circle if they are moving perpendicular to the magnetic field, and then we looked at helical path, and we found that how this motion of charged particles in electric and magnetic fields can be used to where it was used to discover the existence of electrons, and use it as a mass spectrometer, and how we can accelerate particles using these concepts. So cyclotron is one example we have discussed. There are many other kinds of accelerators which you will learn later on in other courses. Thank you.